Hello, we are Senior Design Team 15, Fall 2020, demonstrating our PSSCs for our project. First up, we're demonstrating the functionality of reading SPY packets. We have a script that sends different data over the SPY bus. It'll first do 2 writes, which start with 00, with the address and data following, then 2 reads, which start with 03, then again address and data following. So we will start running that. Here's our setup. We have the Raspberry Pi broadcasting data, our team's board, reading it, and then the analog discovery also there to verify.
We gotta plug this in first, but okay. So the first thing we're going to do is is this USB cable? Oh wow, that's why that's not working. Wrong USB cable. Just a moment here. As you can see, this setup requires a very large number of USB cables, and sometimes it's hard to keep track. So all we're going to do here is use the 82 to record the SPY bus and demonstrate to you guys that we are doing what we say we're doing. And so as you can see, we have one of our SPY, I don't know whether it's a read or a write, but we got a set of SPY packets that are being sent. And if we look at the clock measurements, we can see that this is a 5.8 megahertz SPY clock, which exceeds our minimum requirement for the PSSC of 5 megahertz. And so now that we've demonstrated that the SPY bus is working, we're going to use the Robo probe to read the same data, and we got it all set up for SPY here. And this command is telling it to read 256 packets from the bus. So when we click this button, the next 256 packets will be received by the Robo probe. And as you can see, we have received 256 8-bit packets of data. And the first one is an 033200, and we have an 023142, 0232E0. And these do, in fact, correspond to the sequence of packets we're sending in the application. So this demonstrates that we are able to read data from a 5+ megahertz serial peripheral interface bus. So I think that's about all you need. I've proven to myself. In terms of SPY. I've proven to myself that we can do SPY. Whether or not you accept it is a different matter. So next we're going to do I2C. And can you disable the SPY?
I already did.
Okay, perfect. Yeah, the SPY likes to interfere with things.
Yeah, you send a nice 5+ megahertz signal with a bunch of breadboard wires.
Yeah, it doesn't. It's not happy about that. So next we have an I2C setup, and this I2C setup
We have an Arduino communicating with an Adafruit B&O IMU. Again, both going to the Robo probe and then the analog discovery.
All right, and we're going to put this in a fixed position just so the analog discovery and the Robo probe get the same data. But if you look at the Arduino monitor, you can see we're getting some gyroscope data, and okay, no, apparently we're not getting some gyroscope data. This is not sending or receiving data. Let's see. Okay. Yeah,
there we go.
Okay. Yeah, something errored out, but we're getting data on the I2C bus, and we can use the Robo probe here in I2C mode to see what's going on this bus. So I'm going to tell it to get 256 packets, and in a moment we get those 256 bytes of data, and we can see that we are writing 1A to address 28. And so here we're saying, okay, what address do we want data from on the IMU? We want data from 1A. And then we say, okay, we're going to read from the IMU, which, its address on the bus 28. And then we get this data back, which is our absolute orientation from the IMU. And you can see this doesn't change, where we have the same sequence of, reads and writes as we go down through our bus history here. And just to demonstrate that we're not, magically, pulling data out of a text file or something, we're going to do this for you on the 82 as well. Unfortunately, okay, so this is 0 and 1, right?
Yeah.
Which is clock, which is data?
Good question. 0 is clock.
Okay, so we're gonna turn this off, record mode, and go to a much wider time scale. This is a lot slower, and we're going to do protocol trigger I2C, and okay, there we go. So we can see the exact same, data we were looking at there, where we say, okay, 28 write 1A, and then we do 28 read, and 7B 05 012 00 28 to 0B. And if we look at the Robotrobe, we can see 7B 05 112 00 28 0B. And obviously this was a packet we collected earlier, and this is one we just collected now, but the gyroscope hasn't moved, so its absolute orientation is the same, and it's sending back the same data set. So now that demonstrates that I2C works, and actually let me demonstrate to you that this is indeed I2C fast mode, which is the highest frequency that we said we would be able to do. When you make the measurement on the 82, it demonstrates that clock is 400 kilohertz, which corresponds to I2C pass mode, which is the specification in our PSSC. All right, so now we're going to show you digital waveform sampling at 1.8, 3.3, and 5 volts. So can you set the jumpers are set to 5 volts. So there are physical jumpers on the Robo probe.
Button or switches, really is the term. So currently configured for 5 volts.
All right, and so we are going to show you some 5 volt sampling using the 82 as a wave gen. SPI is off, right?
It is.
Okay, so what we can do here is, now that we can adjust our configuration string that we're sending to the 82, and set it up to sample a digital waveform. And what we just did was command our Robo probe to start sampling on the next rising or falling edge of the input line, which is connected to this function generator. And then if we run it, we collect the sample. And if you look at the 82 software, we are generating a 2 megahertz, 5 volt peak to peak pulse, digital, basically a clock signal. And I have a nice little script here that allows us to plot the output of the Robo probe. And so if we take a look at this output waveform, we can see that, in fact, this is a 2 megahertz signal. So if we zoom in even a little bit more here, we can see that the period of this is 0.5 microsecond, which corresponds to the 2 megahertz signal that we've generated at 5 volts on the Analog Discovery 2. We'd like to show you, some more complicated digital waveforms than just, a clock, but unfortunately, since we need to show this at multiple different voltages, the function generator on the 82 is somewhat limited.
Do you change the duty cycle?
Oh yeah, cool, I can do that.
Oh, but that can be for one of the other voltage.
All right, we'll just do this for 5. So just to demonstrate that we're not bullshitting you by, just getting a CSV file for what that waveform looks like, we're going to change the the duty cycle to 70%, and then tell the Robo probe, hey, we want to see that thing, and then we will start the waveform again. We will yeet the data, and then we will run our plotting script here, and we can see that once again, we've correctly plotted the waveform. Right here, here's one period of it. We can see that is, a 70% duty cycle, and the same frequency that we specified before. So next, we're going to show you that this same functionality also works at the 1.8 and 3.3 volt logic.
Which one do you want to do?
I do 3.3, or we'll go in order. It doesn't really matter, but all right. So we are now on 3.3 volt mode. And once again, we can send a command to the Robo probe to start sampling on the next rising edge, and then we can start at 3.3 volt square wave, and we can send the data to our plotting utility. And, you know, once again, this is still 70% duty cycle because I never changed it, but I suppose that doesn't really, you know, not really the end of the world. And as you can see, we have a 70% duty cycle square wave at 2 megahertz. So now I guess we'll look at 1.8 as well.
And change the duty cycle.
I put it back to 50.
You want?
We can go 30. It is worth noting that when you make the duty cycle on a 2 megahertz function, you know, less than 50%, what you really have is a digital waveform that's faster than 2 megahertz. And so there is a certain there is some error associated with these alternate duty cycles, but the overall period does match. Or wait, let's get this. Are we on 1.5 volt on the level switcher?
Yeah, 1.8.
Okay, so now we can send another plotting command, and we can say not 13, 1.8 volts, and we get some data here that appears to be correct. We send it to our plotting utility, and we have our data. And as I mentioned, when you run a 2 megahertz signal at a 30% duty cycle, you in effect have something that's a bit greater than 2 megahertz. So as you can see, the duty cycle, the timings are not exactly precise, but we have correctly sampled the waveform, at least in terms of the digital values of the signals. And you can see that we have a signal with a half microsecond duty cycle, or half microsecond period, with around a 30% duty cycle, which is, you know, what this intends to convey. So if we look at our team website here, and we say what are our PSSCs here, we say we can read and store I2C packets from a connected bus, and that this will be compatible with standard mode and fast mode configurations. Well, we've showed you the fast mode configuration, and if we can operate in fast mode, we can operate in regular mode, because it's the same exact configuration with a slower clock, so it's, you know, less intensive and identical in configuration. And then for PSS2, we say we can read and store SPI packets up to 5 megabits per second. We just demonstrated us reading and storing a SPI packet up at 5.8 megabits per second. And once again, the machinery is the same for anything at a lower frequency. So we said we could sample arbitrary digital waveforms up to 2 megahertz at 3 different logic levels, and we've demonstrated that for you. We said we can transmit that collected data to the host PC over a USB interface, and that's what we did when we used this application to collect the data and show it to you. And we said we could display the packet data and plot digital waveforms sampled by the Robo probe within a GUI application on a host PC connected to the Robo probe via USB. And obviously, we have demonstrated that functionality. And so, I mean, there's not much more to it than that, I think.